All right, today we are going to finish up 5.2 by talking about thermal energy. So thermal energy is the sum of all the kinetic energy and all of the potential energy of all the particles that make up an object. So your book uses an example of butter sitting on a table. So cold butter sitting on a table turning into soft butter or melting. I'm going to use an ice cube example here. So let's look at situation 1. This will be 2, and this will be 3. So in situation 1, we have an ice cube. The ice cube is what we're looking at. Inside the ice cube, or what makes up the ice cube, are all of these tiny little particles, okay? And all of these particles have kinetic energy. We learned that yesterday. Do they have high kinetic energy or do they have low kinetic energy? Well, because it's a solid ice, they're going to have low kinetic energy. They are still moving. The particles are moving, but it's more like just a slight vibration. They're not shooting all around the way that particles would, say, in a liquid. Those particles would move a lot faster. They would move farther apart in a liquid, right? Then, we'll get to situation 3 in a second. But what we didn't talk about yesterday is that the matter, the tiny particles that make up this ice, for example, this object, they also have potential energy. And this is a little bit different than what we were talking about with potential energy before. The potential energy of particles depends on how far away the particles are from each other. It's the same kind of thing as when I have a tree, or let's say when I have a ball, and I have the ball, here's the surface of the earth, and here's the ball. If it's not moving, the potential energy of this ball is very low compared to, let's say, this ball that I pick up so it's 5 meters off the ground, right? So this ball, the red ball here, has greater potential energy because it's farther from the ground, right? This is the same idea with particles. When particles are very close together, like this, they have low potential energy. Just like when the ball is very close to the earth, it has low potential energy. But when the particles spread out, when they're farther away from each other, they have more potential energy. Just like how when the red ball is farther away from the ground, it has high potential energy, right? So it's the same kind of concept. So as the particles spread out, they increase in their potential energy. Or I guess I would say they have an increase in their potential energy. Back to this. The particles in ice, you can think of them as very closely, tightly packed together. So they're very close. They're like super duper duper close together, like this. So do you think the potential energy of the ice, of the particles in the ice, or the total potential energy of the particles in the ice, is high or low? It would be low because they're very close together. But when we go from an ice to a liquid, or when we go from solid water to liquid water, we are increasing the kinetic energy. That means we're basically increasing the speed of the particles, or the motion of the particles. And the potential energy, if we increase the speed and the motion, we also have to increase the distance between the particles. They're moving around more. So they're farther away from each other. We can't have them moving around more and be exactly next to each other. They have to spread out so that they have room to move. So when this happens, if we have more space between the particles, we have an increased potential energy. So let's think now about the thermal energy of these two, of situation 1 and 2, and then we'll get to situation 3. The sum of all the kinetic energy and all the potential energy of all the particles is the thermal energy. So which one, situation 1 or situation 2, has greater thermal energy? Well, which one has more kinetic and potential energy? The liquid is going to have higher thermal energy because it has more potential and more kinetic energy. This one would have lowest we'll say lower for now. Lower thermal energy. Because it has low kinetic energy, the particles have low kinetic energy, and they have low potential energy. Now let's think about this third situation. So, I want to be very clear, this is called evaporation. We're not boiling the water sitting on the table, right? But imagine like if you spill, I'm sure you've seen this before. You've spilled something indoors where there's no sunlight hitting the indoors spot directly, but let's say you spill just a little bit of water or there's a little drop of water on the table. If no one cleans it up, that water will just sit there, and over time though, it will evaporate. We won't see it. If I left it there for 24 hours and I didn't clean it up, I just let it do its thing, that water is going to evaporate. So it's going to go from liquid to gas. We're not going to see it anymore. So gas, water in the gas form has the highest kinetic energy. Those particles are moving way faster than liquid particles, and they spread out way, way more. So we have way more potential energy and way more kinetic energy in gas particles than we do in solid or liquid. This is gas. Okay? All right, so what would be the thermal energy for this then in relation to the other two? So we are going to have, this is going to be lowest thermal energy. This is going to be now middle thermal energy. And this is going to be, for gas, it's going to be the highest thermal energy. Okay? Because it has the most, the particles have the most kinetic energy and the most potential energy. There are two ways that we can increase thermal energy. Okay? We can either, or we could do both. I guess there's three ways. We could increase kinetic energy. This means causing the particles to speed up, increasing the speed of particles. Or we could increase the potential energy of the particles. That means increasing the space between the particles or moving the particles farther apart. Okay? Or, of course, like we did above, we can do both increase kinetic energy and potential energy at the same time. That would obviously also increase the thermal energy. So those are the three, I guess, ways that we can change the thermal energy, okay, or increase the thermal energy. Or we could decrease the thermal energy in the opposite way, right? If we decrease Ke, we'll decrease thermal energy. If we decrease potential energy, we will decrease thermal energy. And if we decrease both Ke and Pe, then of course we will decrease thermal energy as well. All right? Okay, so that's how we can change the thermal energy. But what does the thermal energy have to do with temperature and heat? And what about the mass? What about how, if an object is super big, what is its thermal energy like? So we're going to look at those three relationships now. You will remember that the temperature of an object is just a measurement of the average kinetic energy of all the particles of an object, of that object, right? And the thermal energy is just the kinetic energy plus the potential energy of all the particles of the object, making up the object. So, what do you think happens to temperature? Well, it depends, actually. If temperature increases, what does that mean? If we increase temperature, then we must be increasing the kinetic energy, the average kinetic energy of the particles. That means, because we're increasing kinetic energy, that means we're also increasing thermal energy, right? because thermal energy is just the sum of all the kinetic energy and all the potential energy. So as temperature goes up, so does thermal energy. And the opposite is also true. As the temperature goes down, what does that mean about the kinetic energy? That means we're decreasing the kinetic energy. So that means we are decreasing the thermal energy as well. All right, so the relationship here is directly proportional. As temperature increases or decreases, so does thermal energy. And the same is true in the opposite direction. As thermal energy increases or decreases, so does temperature. All right, we're going to look next at the relationship between mass and thermal energy. So the mass, remember, is just the amount of particles, basically, in an object. Technically, it's the amount of matter in an object, but remember, we've specified that matter is made up of these tiny particles, aka atoms, ions, molecules, ions, right? So mass is just the amount of tiny particles in an object. And of course, thermal energy is the amount of kinetic energy and potential energy associated with the particles in a tiny in an object. So as mass increases, so does thermal energy. And this might seem like counterintuitive, but let me write that here. Thermal energy depends on mass. Meaning that as mass increases, so does thermal energy. And let's think of an example of this. And obviously the opposite is true. As we decrease the mass, we also decrease the thermal energy. All right. So let's think. Okay, we have one drop of water, a single drop of water. Okay? One drop of water. As opposed to a cup of water that has billions and billions and billions of drops of water in it. This is all water, okay? So, the mass of the drop of water is very tiny. Let's say that it's 1 gram. But the mass of the cup of water, let's say, is 250 grams. So, since thermal energy is the sum of all the kinetic energy and all the potential energy of the particles in that object, or that substance, if we're looking at just 1 gram of water here on the left, do you think that 1 gram of water has more molecules in it that have more kinetic energy associated with them than this mass of 250 grams of water? No. This 1 gram of water has far fewer particles, far fewer tiny atoms, molecules, than this 250, right? The 250 one has 250 times more atoms in it, we could say, right? Well, not necessarily, it's way more than that, but anyway, you get my point. So, the thermal energy of this tiny amount of water is going to be smaller than the thermal energy associated with this huge amount of water. Right? There's a larger mass of water, therefore there's more kinetic energy associated with all the particles. All those particles are moving way faster, they're farther apart, there's more space between the particles because there's more particles, right? So the thermal energy depends directly on mass. The more mass, the more thermal energy. The less mass, the less thermal energy. Now let's look at our final relationship here between heat and thermal energy. So yesterday, because this is later in the book. So we have to define heat. We didn't go over that yesterday. We didn't give it a definition. So heat is the energy that is transferred between objects due to temperature differences between those objects. So let me write that down. So this is different than just hot or cold or how it feels, right? And we kind of have to to make our brains like forget what heat means to us in non-scientific terms in order for this to make sense. So warmer objects, what this is basically saying is that warmer objects always heat cooler objects, but the opposite can't occur. So an example is, let me write that. And so there we go. So warmer objects always heat cooler objects. But cooler objects cannot heat warmer objects. So the example, the easiest example, is you put a pot of cold water on the stove. All right. So our colder object is the pot of cold water. And we're going to put that on a stove, and we're going to heat that stove. Okay. So we're going to have this cold object sitting on this hot object. This cold object is not going to cool that object, cool the hot one, right? It's going to do the opposite. This hot object is going to heat up the water. It's going to make the water hotter, right? So the heat transfer goes from areas of high heat to low heat. This is an important thing, and we're going to see this over and over and over again in your study of science. This is called a gradient. Gradient. Okay? So that means the gradient literally just means areas of high, in this situation, heat to low heat. But we could also have it in there's lots of different gradients that we have in science, but this is just probably the most simple and the first one that you usually learn. So this gradient is an area of some high amount to a low amount. We're never going to have the low amount. We're never going to have this flow from low heat or cold to hot, right? The heat is always going to be transferred from the high heat to the lower heat. We're never going to have this cool pot of water cool the stove, right? Another way to think about this, maybe without the stove, since it has a constant source of electricity, let's think about a cup. Let's think about a cup of tea. Okay, there's my tea. Tea's in there. It's super hot. It's steaming. Super hot tea. That's supposed to be steam. There, that's a little prettier. Okay, this super hot tea, okay, is steaming. It's so hot. The cup is hot. Everything is hot. I'm going to set this tea on my table, my wooden table here. Okay? Over time, all of the heat associated with this tea is going to be transferred to the cooler table, right? So the tea does get cooler, but it's because it's transferring its heat to the table. The table isn't transferring its cold to the hot tea, right? It's only going from this area of high heat to this area of low heat. And over time, they'll eventually be the same and they'll equal out and there won't be a gradient anymore. But at the start, this high heat area is transferring heat to the low heat area. This is called a gradient, okay? All right, so what does this have to do with thermal energy? Well, we learned yesterday, let's just go down here. We learned yesterday that heat, where did we learn that? Here. We learned that heat and temperature and kinetic energy are all directly related, right? Oh, look, I used hot tea yesterday too. I don't even drink tea. But anyway, so heat and temperature and kinetic energy are all directly related. We said that as temperature is increased, heat is increased, and so is kinetic energy. So if we're thinking about thermal energy now, well, increased heat means increased temperature. What does temperature mean? Temperature means increased kinetic energy, right? Average kinetic energy. Well, if we have increased average kinetic energy, then we're also going to have increased thermal energy, right? Because thermal energy is just kinetic energy plus potential energy. So the relationship is that as thermal energy increases, so does heat. As heat increases, so does thermal energy. As heat decreases, so does thermal energy. And this information that I was giving you about the gradient, this doesn't necessarily, I was just trying to explain to you the way that heat works and the way that it flows down a gradient. So tying back into our original topic, which is how does heat relate to thermal energy, it's right here. But you have to kind of understand what heat is and how heat works in order to understand all of these relationships that we're talking about. Now we're going to talk about this other concept called specific heat. And from your reading, you should hopefully kind of understand specific heat. Specific heat of any material is the amount of heat needed to raise the temperature of 1 kilogram of that material by 1 degree Celsius. So let me write that definition down. All right, so that seems like maybe kind of a complex definition. So I think it's easier to look at some examples of this. So let's look at the beach. We're going to think about the beach and the sand and the water, okay? All right, so let's think about when we're at the beach on a super hot day. If I stand here in the sand, my feet are going to get real hot, right? The sand feels super hot. But if I walk down and I stand in the water, my feet don't feel hot, right? The sand is hot, but the water is not. Why is that? Well, because the sun is hitting the sunlight, the energy from the sun, the radiant energy from the sun, or the light energy from the sun. It's hitting the sand the exact same amount as it's hitting the water, right? Like they're in the exact same place. It's not like the sand is getting more sun energy, right? So why do they feel differently? Why is the sand hotter than the ocean water? The reason for that is because the specific heat of the sand is much lower than the specific heat of the water. The specific, which I should tell you, we abbreviate specific heat as SP, like that. Is that how they do it in your book too? I think that's how they should do it. Oh, they might do it as Q. We'll come to that later. No, they do it as C. So we'll call it, since that's how it's done in your book. So specific heat is abbreviated as C. So the C of the sand, that's funny, is 830, and the units on that are joules divided by kilogram times degrees Celsius, while the specific heat of the water is super duper high. Compared to that, it's 4,200, and the units are joules times kilogram, or divided by kilogram degrees Celsius. So let's break down what specific heat really means in this instance. So in order to raise 1 kilogram of water, let's say this is 1 kilogram of water, and let's say this is 1 kilogram of sand. Okay? In order to raise the temperature by 1 degree, so let's say our starting temp is 20 degrees Celsius. So to raise that temperature of this 1 kilogram of water, to raise it to an ending temperature of 21 degrees Celsius, and the same with the sand, we're going to say the sand starts at 20 degrees Celsius, and we're going to raise the temperature to 21 degrees. We're just going to increase the temperature by 1 degree. In order to do that, we must have 4,200 joules of energy going into that water. Whereas over here with the sand, the specific heat of the sand, we only need 830 joules of energy going into that 1 kilogram of sand in order to raise it 1 degree. So we need a lot more energy going into the water than we do going into the sand in order to raise it. We need I don't even know, is that 4.5, 4-ish times more energy going into the water than we do going into the sand in order to raise it just 1 degree. So that means another way of thinking about this is we would need way more sunlight just to go over here into the water than we would for it to go into the sand. We would have to block the sand off so it's not getting as much energy, and we'd have to put all of the energy from the sun going into the ocean in order to make these two equal. But that's not the case at the beach, right? We don't have that. We don't do that at the beach. That's not possible at the beach. So the reason that the sand is so much hotter is because it has a much lower specific heat than the specific heat of water, which just means that the water requires way more energy to raise its temperature than the sand does. There's a very nice table in your book that looks at a bunch of different specific heats. We look at the specific heat of water, which we already have, and we're comparing it to wood, sand, and iron. So the specific heat of water, we know the units. We'll say the units are, I'm not going to write the units every time. So the units for specific heat. All right, I'm going to move this table. All right, so we have 4,200 for water. For wood, the specific heat is 1,700. So it takes 1,700 joules of energy in order to raise the temperature of 1 kilogram of wood by 1 degree Celsius. For sand, we just looked at that, it takes 830 joules of energy to raise the temperature of 1 kilogram of sand by 1 degree Celsius. And for iron and lots of other metals, we'll talk about other metals too, it takes only 450 joules of energy to raise the temperature by 1 degree of just 1 kilogram of iron. So iron and other metals all have a very low specific heat. They all have low specific heats. So what that means is that it takes very little energy for their temperature to be raised. As opposed to water. Water is pretty much the substance with the most common substance with the highest specific heat. And this is why water is used as a coolant. A coolant in a lot of situations. Water is used. And a coolant is something that cools down other substances. So cars, well, I don't know if cars do, but I think they do. Engines, a lot of engines use water as a coolant to cool down the engine. And the reason for that is because water can absorb a huge amount of thermal energy with very little change to its temperature. AKA, it's because it has a high specific heat. All right, so I'm going to write down what I just said. Again, water it's useful as a coolant because it can absorb a huge amount of thermal energy with a very small change to its temperature, with only a little bit of temperature change. All right, so there's that again. So it's used as a coolant because it has a really high specific heat. If we look at this compared to all the others, it's got a super high specific heat. And what that means when you have a high specific heat is that the substance can absorb a very large amount of energy while having its temperature change very, very little. All right, so we are now going to look at some ways that we can calculate thermal energy using the mass, temperature change, and the specific heat of a substance. So we have an equation for this. And I'm going to write it all out in words, and then I'm going to give you the equation with the abbreviations. So we have change in thermal energy equals the mass times the temperature change times the specific heat. All right, so this is going to be measured in joules because it's energy. This is going to be measured in kilograms. This is going to be measured in degrees Celsius. But I'm probably going to give you tricky questions with Kelvin or Fahrenheit like we did yesterday. And this is going to be measured in the same units, kilogram times there. Okay? All right, so the simple way to write this is thermal energy, or change in, anytime, should I introduce you to this? Yes, I'm going to introduce you to this. This is another very big, so we learned gradient today, and we're also learning this idea called delta. Delta literally means change in. Delta is the Greek symbol. It's this little triangle, and it means change in. Okay? So, change in is delta, and thermal energy is abbreviated Q. So if I said, what is the, if I wanted you to abbreviate this, you would say delta Q, which means change in thermal energy, is equal to little m, mass, times temperature change, or change in temperature. So how do I write change in? Delta T times, we already learned earlier that C is specific heat. All right, so delta, you're going to see this 10,000 million, 100 billion, quadrillion times throughout your scientific career. So delta is very important, that you understand that it means change in. All right, so when we have change in like this, this change in delta T is equal to the final temperature minus the initial temperature. Okay? Delta Q is equal to the change in thermal energy, which would be the final thermal energy minus the initial thermal energy. All right? So rather than writing QF minus QI equals M times TF minus TI times C, too much, we do change in. All right? We do delta. So, but you need to understand that a change in just means, I mean, when I was 5 years old, 5-year-old Miss Montgomery, she is, let's say, I don't know how tall is a 5-year-old. Well, I don't know how tall a 5-year-old is. Let's say I was 1 meter tall. I was a tall 5-year-old, I guess. And as a 30-year-old Miss Montgomery, I'm 1.7 meters tall. I've grown. 1.7 meters. Okay? So my change in height is going to be my final height that I'm at now, which is 1.7 meters, minus my initial height, my height initial, right? Minus 1 meter. So my change in height is 0.7 meters. It's the same concept with temperature and with thermal energy. So just the final situation minus the initial situation. Maybe I'm beating a dead horse and you understand this, but just want to be extra super clear so you understand what I'm talking about when I say change in or delta. All right, so let's do a practice problem using this very nice equation right here. All right, here we go. Example. A wooden block has a mass of 20 kilograms and it has a specific heat of 1,700 joules per kilogram times degrees Celsius. Find the change in thermal energy as this block warms from 15 degrees to 25 degrees Celsius. So let's write all of these things out as knowns and unknowns, which some of you are still not understanding that you're not going to get full points for things if you don't write this out. So I've stopped telling you that you need to write these out every time because we've been doing it for 3 months now. So you must write this out every time. You must show your work on your homework assignment. When you just write an answer, you're losing points. And a lot of you don't really, shouldn't be losing points like that. Super easy points. So anyway, let's write down everything we know. We know our mass is 20.0 kilograms. We have a specific heat of 1,700 with the right units here. So this is the part where we need to think about our final temperature and our initial temperature. It's pretty easy when it's like this. We can see we're warming from 15.0. So that means we started at 15.0. So that means our initial temperature was 15.0. And our final temperature, or we're going to a temperature, so our final temperature is 25 degrees Celsius. In this situation, it's pretty simple to see that our delta T is 10 degrees Celsius, right? Because TF, which is 25, minus 15, which is TI, is 10 degrees Celsius. Maybe in the future, you might have to actually plug this into a calculator to figure it out. But it's pretty simple. We just take our final temperature and subtract our initial temperature from it. So here we have 10 degrees Celsius, and they're asking us to find delta Q, the change in thermal energy. We're going to use that equation that we just got right there. So it's going to be mass times delta T times specific heat. We don't have to actually change anything here, but be aware, sometimes this might be given to you in a different unit. If I gave that to you in Kelvin, you would first have to convert this to Celsius before you can go on, right? Because we have Celsius right here. We can't have Kelvin mixed in there in the middle. Or maybe I'll give you the mass in grams and you have to convert it to kilograms, right? So just be aware, make sure everything is in the right units before you move on. All right, so let's solve. We have delta Q is going to equal 20 kilograms times a change in temperature of 10 degrees Celsius times a specific heat of 1,700 joules times... Okay. So let's think about how our units are going to cancel. Our kilograms will cancel our kilograms. Our Celsius will cancel our Celsius, and we'll be left in joules, which is great because we are talking about energy, and that's what energy is measured in. So our change in thermal energy, if we plug all of this in, we will find that our change in thermal energy is 340,000 joules. All right. Okay. So that is, I think that's it for the chapter. Yep. We are not going to talk about how we measure specific heat with a calorimeter. We'll get to that in chemistry. So, all right. So that is it. So today, for the rest of the period, however much time there is, and for your homework tonight, you're going to work on the 5.1 part 2 questions. And you're also, tomorrow you'll work on some 5.1 review questions. And that is it. This is going to be a kind of more, we're going to involve everything, we're going to include everything that we've learned in 5.1 in these questions. So we'll look at, there will be more tricky questions like I was just telling you. Like I will give you degrees, change in temperature in kelvins, and you'll have to convert that. So tomorrow, this is the assignment that you'll be working on in class, and it's going to be everything combined from 5.1. But today, it's just, the assignment is just over what we've learned in the second part of 5.1. Please let me know if you have any questions. Please hand your work in on time. This assignment is due exactly at the start of class. The late policy will not apply, meaning that if you hand it in at 3 p.m., you get a 0. There's no minus 5%. You have to hand this in before the start of class tomorrow because I'm going to go over it in a lecture tomorrow. So be sure you hand it in on time, please, or you get a 0. And many of you, again, can't have any more zeros. Let me know if you have any questions. Thank you.